All right, so keeping in line with our previous example and talking about how the differential equation is equal to a rate of change, all right, then what we've got here is a little bit of a different form of that. dy dt equals k times y, where y is going to become y0 when t is equal 0. In other words, y0 is your initial starting amount. So if we apply everything we did on the previous slide to what we're getting ready to talk about here and make this substitution with k and y0, then you have that y, okay, your total amount, is equal to your initial value times e to the kt power. K is a constant, it never changes. T changes, your initial value doesn't change. So what we're going to be able to do with this is identify a way to keep track of money that's growing in a bank, for example, or something that grows exponentially, okay? And what we're going to look at with this next example is specifically money in a bank, but you could use this to find how rates of change occur with different bases, how something, different fungus or whatever, or mold multiplies and grows. There's all kinds of different ways that you can use this, okay? So continuously compounded interest involves E, and if you have interest that's compounded at different set periods of times, that would be referred to as the K. All right, so let's look at this continuously compounded interest part. If you invest a sub $0 or an initial amount of dollars, notice this is very similar to our previous problem, our previous rule from right here. Okay, if you invest a $0 into an account with a fixed annual interest rate R, and if the interest is compounded K times a year, then the amount of money represented after T years is going to be this equation right here. So we're going to use this equation a lot in the next few minutes, okay? But there's different ways that we would figure compounded the interest continuously, okay? So we can model growth of our money with a differential equation that has this initial value. So here's our differential equation with our initial value, and when we follow the path down, just like we did on our previous problem, if we follow this path down right here, what happens is we end up at this problem for finding the amount of money after T years. So we solve the differential equation, we substitute in our initial condition, which was that T is equal to 0. And what happens is we end up with this formula down here for continuously compounded interest, okay? So now the question becomes, suppose you deposit $800 in an account that pays 6.3% annual interest. How much will you have after 8 years if the interest is compounded continuously and quarterly? So we would set up with y equals A0 EKT for part A. All right. And for part B, we set up with y equals A0 times 1 plus the rate divided by K to the KT power, okay? So these are the setups for these, and we're told the rate for both of these is going to be 6.3%. Well, we have to have our rate as a decimal, so 0.063, same for this guy, 0.063, okay? And we know that our initial value is $800, so A0 is equal to 800. Okay, so how much will you have after 8 years? Well, we've got this set up. One last thing, T is 8. I don't know why my tablet's making those wiggles. I don't feel like I'm writing that way. So now what we have to do is get your fancy dancy calculator out, plug these values in, plug them in carefully, and see what you get. So in this case over here, we'll switch it up a little bit in the pink. Y equals 800 times E, and then for the exponent, 0.063 times 8. So I'm going to punch that into my calculator real quick. We'll just work these bad boys out one at a time. So here we go. 800 times E.
Thank you for saving my cup.
800 times E to the 0.063 times 8, which is going to be $1,324.26. That's how much we would have after 8 years if we just start with $800. Okay. On the next guy, we'll solve him out in purple. What we're going to do is we're going to say that y equals 800 times 1 plus the interest rate 0.063 divided by k. That's the number of times that we're going to compound interest, which is 4 times a year. And then we're going to raise this to the 4 times 8 power. So I'm going to punch that in, and we should get a number that's similar, but not the same. It should be a little bit different. So 1 plus point. All right, and on this guy over here, we end up with $1,319.07. So, interesting story here. There's not a large difference between these two, even though one interest is compounded continuously and the other one's only compounded 4 times a year. But this is how you would look at some of those different rates of change, starting from the differential equations that were at the beginning of this lesson.